Oh yeah, this is actually like my 4th recording attempt. It's pretty bad. We had lots of problems this morning, but just a note for y'all and for the video too is that there is a like take-home test basically. So like the chapter 6 mini test or whatever is due today. Maybe I'll go in there and switch it to at least by tomorrow night or something. But you need to take care of that. And then, yeah, we'll have another little worksheet that we'll do after lunch and get all that taken care of. But make sure you're doing that. So what we're going to do is we are on whatever that first page, part 1, and I'm just going to jot down some ideas, and then we're going to do part of the check your understanding, and then we'll get into like the part 2 of the lesson, which this is kind of starting to get into what we're going to do for the spring, a lot of the main idea. And it almost feels like a math class, like you start doing more actual calculations and like numbers. It's weird. So if you like that or not, that's what's going to be happening. Okay, let's get just some general ideas here first. An important idea. So let's talk about some symbols first. That would be good. So let's talk about symbols. I don't know how to spell. Symbols. So some important distinctions, because we're going to start doing like inferences about our population, but with a sample. So you need to know the different symbols with like population and sample. So yeah, all right. I'll give myself some room here. So we're going to do it for some symbols for proportions, means, and standard deviation. And I'm going to do the symbol for your population and a sample. This is taking up more room. Okay, so I'm going to do what's the symbol for our population for a proportion. So a proportion is just like 5 out of the last 7 flips of the coin were tails. So proportions are listed in fractions or percentages or decimals. So like when you think proportions, those are those percentages or fractions. The main symbol for that, if you're talking about the population, is just P. So like P equals 42% of them were heads, of the tosses are heads. Or coin tossing would be 50-50, so P equals 50%. The sample is P with a little caret, so it's actually called P hat. So like P would be, yeah, the population parameter proportion would be 50-50 on flipping the heads, but maybe I got a P hat of 45% heads or whatever. Okay, the means or averages, like the average height of Brian High, the population would be that symbol we've used kind of throughout in some times, which is it's called mu, and then the sample mean is x with a bar over it, and it's called x bar. So it's your sample mean. And then the population standard deviation is that symbol we've used, like an O with a line. And then the sample standard deviation would just be like an S. So we'll use those more, just if you're come in contact with them. I don't want you to be afraid. All right. So when we're going to do this unit called sampling distributions, and what it's going to do is, like, for a big population, like even Brian High with 2,000 students, it's pretty hard to go around and collect the average height of Brian High, to get every single student, all the at-home kids, whatever, the average height of the US. So we do a sample, and when we do a sample, we don't just want to do one, we want to do like many samples over and over again. And so we want our samples to be good representations of our population. And so two things that we're looking for in a sample is that we obviously want them to be unbiased samples. So you take like a good random sample, so like an SRS or a cluster sample or a stratified sample, like your sampling questions are not bad. We want them to be unbiased estimators. So like unbiased would mean, let's see. I ended up doing this in second period. It worked out okay. So like think about like a target. This is pretty simple on this case. So like unbiased would be like when I'm shooting at this target, like the center of my things are like hitting where I'm aiming. Like it might not be perfect, but it's like hitting my target. So that would be unbiased. But biased would be like maybe I have a tight spread, but like it's like missing the mark. So like even no matter how good that I get of a shooter, if I'm not aiming in the right spot, I'm not going to get it. Even if I get really tight cluster there. So that's like biased basically. You're missing the mark. That's unbiased. Okay. You also want there to be low variability. Low variability. So low spread in where your samples are. So like if I'm doing a sample of, let's just use the example again, a sample of the height of people at Bryan High, the average height. If I do a sample size of 2 people of Bryan High, a random sample, I might accidentally get a random sample of the 2 like shortest people, and then it's like really low. And then if I do another 2, it might be really the 2 tallest people. So my spread's going to be really big. If I do a sample size that's bigger, like if I sampled 20 people from Bryan High, I'm going to get a mixture of some low height, some high, but it's going to average out that mean, that sample mean, if that makes sense. So low variability, the way that you counteract that is that you want your samples. So the way we're representing sample is N. You want your sample to be, the bigger it is, the tighter the spread is, the smaller your spread is, because the averages or the proportions like cancel each other out, the highs and the lows. They like average out into one. So I want my sample size, N, to be like high. Oops. Not necessarily a great thing. So like an example, let's just use the target again. So like, here's my target. Let's say the sample size is 2 or whatever. Maybe this isn't the greatest. Maybe let me do the dot plot for this one. So if I did a dot plot of sample size 2 of the heights of Bryan High, I'm going to get a couple people that were both low, some people that were high, and like I'm probably still going to average out around the mean, but it's going to be more spread. If I did a sample size of 20 people, here's a average height of 20 people, the next average height of 20 people, the next average height of 20 people, and those are going to be more stacked up in like a tighter window, lower variability. So the bigger the number, the higher the spread, the lower your sample, or the higher the sample, the lower it is. So those are just some general things. We're always looking for unbiased, and we don't want a lot of variability. So an easy way to do that is have a bigger sample. But you don't want to have too big of a sample, because then things aren't independent. Like we talked about, less than 10% of your population. So there's kind of a mix. Okay, so let's talk about, I'm just going to do number 1 on the check your understanding, because I just figured from second period, like the more of an example that we do once we get into this next page, just the better it'll be. So on this one, check your understanding, we're going to go through like what these words are, what we're looking for. So let me just sum up this nice hefty paragraph for you. This is like pennies that were made in 1982 have a higher percentage of copper. And so Jenna is wondering how many of those pennies made prior to 1982 are still in existence today, like haven't been thrown out. So she read online that 13.2% of pennies in circulation are pre-1982. So she has a large container at home. She did a random sample of 50 pennies, and she found that 11 of those 50 were pre-1982. Does this provide evidence again? So some words that we're going to go, so population and sample. So what's our population we're looking at, and what's the sample that we took? So our population in this case is, what did our sample choose from? What were all the possible things that we were choosing from? It was basically Jenna's pennies that she had in her large container. So our population is Jenna's large container of pennies. So like that's our population. That was what we sampled from. Our sample was 50 of those, so we found 50. So 50 pennies from the jar. Okay, so parameter and statistic. So parameter is, what parameter is it is a number or a value from your population. So it's a number from your population. So like the actual average height of Bryan High, the true percent of people at Bryan High who drive a car to school or whatever. Like whatever it is, it's the number from our population we're looking from. And the statistic is a number or value from our sample. So like I found in my sample of Bryan High students that the average height was 5'5", like whatever. So parameter, easy way to remember it is like P, parameter with population, S is statistic, S sample statistic. So S goes with S, P goes with P. So like in this case, what's our number that we're interested in, that we're like looking for from our population? We were comparing that like 13, so that our proportion was 13%. So I'm going to go for the decimal, 0.132. So I guess specifically that P equals 0.132, and P in this case is that pennies pre-1982. The statistic is our P hat, and it was that Jenna got 11 out of 50, which we like to put these into decimals, like in general. So 11 divided by 50 is 0.22, so 22%. So just some basic words that might pop up, might see, or just some terminology, but parameter, getting the correct population, what's your sample, just identify. I'm going to kind of leave that page at that. That will be good. So let's go on to that Reese's Pieces page on that other one. And we're actually going to like do a problem here and like set up a simulation of what's happening. So a simulated like sample from our population. So what we have is, if we take a sample of Reese's Pieces, what's the proportion of candies that will be orange? And so unfortunately in COVID days, a lot of these things in the spring, like some of them occasionally have candy that I like used to bring, but I don't think I'm allowed to do that, like give y'all stuff, so that kind of stinks. But what's the proportion of Reese's Pieces that will be orange? So if we open the bag, what's the percent that's going to be orange? And so we're always kind of like given a claim, or like a company thinks this, or we assume this, and that's kind of like our population. So suppose we have a large bag of Reese's Pieces that has 1,000 pieces. The manufacturer says that exactly 40% of them are orange. So like when they put a bag together, they're counting. 40% is what we have. If we select a sample of 50, how many will be orange? ... So what I actually want to do on this is, the front side of this paper is like the same as question number 7, 8, and 9. So we're actually going to skip. But on this part, I want to just point out like what's our population. So you can write this in the number 1 section if you want. So like, what's our population? What's our sample? What's our parameter? What would be our statistic? Because there's like the offhand chance that on an AP test they could ask, and we wouldn't want to get something like this wrong on like identifying some stuff. So population in this case is like, where did our sample come from? Like, who is this taken from, or what? And so in this case it was the large bag of Reese's Pieces. So it would be our large bag of Reese's Pieces, orange pieces. And then our sample was a sample of 50. So there is a parameter because the manufacturer says this, or somebody's claiming this, a newspaper claims this, we assume this. So the parameter was that we think the proportion, or P equals 40%, are orange. So we think 40% of this bag is orange. And our statistic, which we don't have one, we're going to get some. Our p hat would be like whatever number we got over our sample of 50. So we're going to do that, but we're going to run a simulation to do a lot of trials of 50. But like a statistic would be one of those samples of 50. So if you got 20 out of 50. Okay. So let's look at the back. If you flip over to number 7 and 8, I've got a nice little computer simulation that we can do up here that does zoom out here. That kind of simulates our experiment here. So this is like, let's say this is our large bag of Reese's Pieces that have 1,000 in them. So I've set it up to where our probability is 40% to get orange, and we're choosing 50. And this is just saying like how many samples. So like I'm going to do one sample of 50 is what this is going to do. So I'll show you the animation here. So like I'm clicking it and they're splitting them like orange, other, from the sample of 50. And on that one sample, they got a p hat equal to 42%. So like that would be one of our sample statistics. So what we're going to do is, like I could have y'all pull up this applet and do them and we can make a dot plot. What we're going to do is just kind of make one together here. So I'm going to end up doing like a lot of different samples, and we're going to make a simulation of like what would it look like. So we're going to do a simulation of p equaling 40%, and what would it look like to get all these different p hats of like sample size 50. So simulation of p equaling 40%, doing sample 50. And so what we're going to get is a ton of little p hats here. So what's going to happen is, let's just check this out. You don't worry about writing down every single one that you get. Let's just make a general one when we see it at the end here. So I'm not going to animate it. I'm just going to pull up a dot down here. So I'm going to draw the sample, and that one was 56%. So that was like, they opened up they drew another 50 and they got 56%. Does that make sense? Like they re-put the things back in there and drew another 50. Okay, so they're going to draw another sample of 50 and they got 42%. Another sample of 50, 28% of them were orange. Another sample of 50, 44% of them were orange. Another sample of 50 and they got 46%. So they're going to do more and more and more. So like right now, my little dot plot down here, I've got like 26%, 34%, 36%, 38%, 42%. Got all these different possibilities of what's happening. And this is like just doing a few. So on a simulation, the nice thing about doing a simulation is that we can simulate a lot of trials really quickly. So like right now, this is only as if like 10 of us had done it. But it's really nice in statistics to do like a repetition really quickly. So like I'm gonna go up by like 20 here. So like I'm gonna draw, and now you can see like the total amount sampled is 30, so we've added 20 more dots, and it's becoming a little clear where our like average might lie, what our thing might look like. So I'm going to draw another amount, and like here's the simulation of what it would look like at 40% being orange. You could get up to like 56%, you could get a sample of like 26%. So let's see, let's go to, I'm going to do 50 to get up to 100. So we've done 100 total simulations right now. And this is like what my graph looks like. So I have some over here, a lot here, and then it kind of tails away again to the right side. So kind of a way to put this is that, I think number 9 asked this on there. It says like, what does a dot represent on there, right? Yeah, what does each dot represent? So like, what does this dot represent right there? Like every single dot. So every single dot represents basically a p hat, which means in this case, a p hat was a sample of 50 rhesus and like the proportion of orange that there were. So like every single one of those dots is its own p-hat, its own statistic. Here's another sample of 50. Another sample of 50. Like every single dot is just piled up at like a certain p-hat. So you could almost write these instead of dots, you could like pile them up as a bunch of like p-hats. Like here's all these different possibilities that you could get. So some things that you can do with this that we'll kind of get to is like, let's say I did a sample of Reese's and I got a p-hat that was equal to like 62%. Does it seem likely? Like, was my package weird? Like in this case, my package would be super weird if I got 62% orange. But if I got a package that was like 48% orange, maybe that's not as much weird. Or if I felt like I got gypped and only 32% of them were orange, that could happen by chance. So I can kind of run a simulation. Like if I only had a bag with like 20% orange, then yeah, something probably went wrong. So you can kind of use these simulations to get like, if I'm supposed to have a P equaling to 40%, how likely was it for my sample to pop up by chance? Is kind of the goal of these sampling distributions. Okay, so let me come back here. So if you want to, you could kind of sketch what that was, point out the dot plot, just kind of, they're your notes, like you can use them as you'd like. So we're gonna do like, where is the mean and standard deviation of this graph? So this simulation that we just ran for a parameter of 40%, where is the mean at? Where's the standard deviation? So if you picked up, hopefully you picked up a formula chart, and we're gonna check that out. I don't like that I put a different one on Schoology, but on the formula chart, which they were on this other table. Maybe you didn't need that. You do need that. Yeah. So if you didn't get one, so what we're looking at is on the back side of it. So if I flip over to the back side, up at the top of y'all's it says sampling distributions, inferential statistics, which is what this one says. Y'all's looks slightly different. What this has is it has it for one sample p-hats, two sample p-hats. It also has the same thing for means down here. So it has one mean, two means. It has these different formulas or like that we'll use. So what we're doing is we're using proportions, so p-hat. So this is our formulas that we're going to look at right here. We have one sample, a sample of 50, whatever, and it says the mean, wrong one. So the formula says that the mean of p-hat is supposed to equal p. Let me put that into words. That means the average of all of those p-hats in the simulation we just did is supposed to equal our population parameter. So on that Reese's Pieces thing, the average of all of those p-hats, all those dots that we did, should have averaged out at 40% or about. Like over many, many trials, it will average out at 40% in the long run. So basically, the mean would equal 40% in this case. Like that's what we would say. the mean of all of those sample p-hats is 40%. And then, like with anything, there's standard deviation, there's some spread. Like, you don't get the same answer every time. There's variability. So the formula says do the square root of p times 1 minus p divided by n. So in our case, this is always the population, what we're assuming. So the p is, we're going under the assumption that we've got 40%, 0.4 rhesus, times, you could write 1 minus 0.4, or you could just write 0.6. So 0.4 times 0.6 divided by a sample size of 50. Which is, on decimals, let's go to 3 decimal places. So I got 0.069 would be the standard deviation. And just to kind of, again, relate it back to this thing. This is talking about this distribution right here. Like if I kept doing more of these, draw more, draw more, draw more, like we're saying that these are all a bunch of p-hats. These average out at about 40%, and they have a standard deviation of 6.9%. So that seems to kind of make sense, possibly, maybe. Okay, we're going to talk about what's the shape of our sampling distribution. And so on this, I've got a nice peak. I've got a tail to the left, a slight tail to the right. Maybe if I did some more, it would become a little better. So it's kind of not perfectly symmetric and normal, but it's approximately normal, which is great. We want to do, in statistics, we want to get stuff into that. So there's a way to prove that we have to do. So what's the shape of it? I learned in second period, I don't know how to spell anything. It's because I abbreviate a lot. So I'm just going to abbreviate again, approximate, because I think I put an I, it might be an E. I don't even want to think about it. But approximately normal. And the way that we show that, you have to do a check. Kind of like we had to check with the binomials. You have to do a check where you show that basically that your sample size compared to the proportion is big enough. So we have to do that sample size times proportion is greater than or equal to this number 10. And that sample size times 1 minus the proportion is greater than or equal to 10. And it basically, what this is that ensuring that our sample size is big enough compared to our proportion. So that we're doing that 50, a sample size of 50, and doing another sample of 50, another sample of 50 was big enough. So in this case it would be 50 times 40% is 20, I believe. And 50 times 60% is 30. Both of those are bigger than or equal to 10, so it would just be boom, we're normal. This is an approximately normal shape. So we have to show this to prove that it's normal, that it's a big enough sample size. So this is helpful because this guarantees that if my population is skewed, that my samples are normal distributed. So even if my population has skewed data, the sample distribution, all those sample p-hats become normal, which we might look at that. let's try a problem out. So on number 12, we know that the bags of Reese's contain 40%. If we did a random sample of 50 candies, what's the probability the sample proportion will be 50% or greater? So what I have is I just proved that I have a normal distribution, mean, and standard deviation. So I'm going to draw a normal distribution, and it should be centered around that 40%. And maybe I'll make a note that my standard deviation is what it is. Okay, our question is, what percent of this normal distribution with this standard deviation has 50% or greater? Alright, so we are gonna dip back into like z-scores and using our table and getting stuff that way. So we're going to be doing that for this unit, confidence intervals, hypothesis test. So we're going to get back into that. So we're going to what we're going to do is we're going to standardize this score and then, or this thing compared to same, like how many total standard deviations is it away, and then use our table to look at it. So a reminder on z-score is that it is like your value minus the mean, so the distance you are from the mean, and then how many standard deviations is that? So divided by standard deviation. So I want to standardize what this 50% is in comparison to this setup. So it would be 0.5 minus 0.4 divided by 0.069. Which ends up being like 1.449, and the z-table goes to 2 decimal places. So for the z-score, round to 2. So 1.449 would be 45. So that's like our z-score, a positive 1.45. And so then I'm gonna go to my formula sheet, or in class y'all have it in 2 different spots, 2 different papers, and we look at our normal distribution z-table, and I'm going to go to the positive z side. I'm going to go to z equals 1.4 and then 5, so 1.45 is 0.9265. But remember that this is always talking about the area left of it. So where's the 0? So I'm just going to say that like the table value gave me 0.9265. But that's like this value over here, which I don't want. I want the red, the greater than part. So you have to do one more step. So to get greater than, this is 92%, so you have to do 1 minus it to get the leftover part. So 1 minus 92%, whatever, is 0.0735. Like, decimal answers are fine, but I know that percentages make a little more sense sometimes. So like, that just means 7.35% of all possible simulations. If I had a mean of 40, 7% are bigger than 50% orange. So that's like the percent chance of getting that many orange. For whatever reason, if you really want orange Reese's Pieces, those are the ones you like. They taste better. What are they, yellow, brown, orange?
Mm-hmm.
Okay, so that is one idea. So we're gonna leave it at that. After lunch, we'll do another example on the check your understanding, and then y'all can work on a worksheet. But we're gonna stop there for that little part. So yeah, so we got just basically proving that it's normal. The idea is, though, to kind of go back to it, is that we just like ran, they figured, they told us that it's like 40%, so we just did a simulation of if it truly is 40%, where would, like, what's the spread of values that I get? Like, what do they look like with a sample size of 50 with a proportion of 40%? So like, how far did they go, left or right? Yeah, so that's the general idea.